Hello everybody and welcome back to another video. In this video we explore the topic of multiplying radical expressions. So to begin, let's consider the following two expressions. Suppose that we look at the square root of 4 times the square root of 9. So we know how to simplify each of these. The square root of 4 is 2, the square root of 9 is 3, 2 times 3 is 6. So the square root of 4 times the square root of 9 is just 6. Now let's also look at the following. Let's take a look at the square root of 4 times 9. Well, the square root of 4 times 9, all under that radical, we would get the square root of 36, which also turns out to be 6. So this actually leads into a more general property. It's called the product rule for radicals, and it's written in the following way. If we have the nth root of a number times the nth root of another number, we get the nth root of the product of those radicands. So we get the nth root of the product of A and B. So the nth root of A times the nth root of B is just the nth root of AB. So that's the general rule that we've just gleaned from taking a look at the above example. Now, let's take a look at some more examples. So I'll pan over to the right. Let's consider the square root of 2 times the square root of 7. Well, we just apply that rule. Remember, no matter what the index is, here it's a square root, so the index is 2. No matter what your index is, you just, as long as they're the same index, so here it's a square root, here it's a square root, so the index is 2 in either case. As long as those indices are the same, then you can just multiply the insides together. So we just get the square root of 14. And this can't be simplified or anything like that. But let's take a look at another example. Let's suppose that we've got, let's just letter this A. Let's suppose that we've got the square root of x plus 3 times the square root of x minus 9. Now, we just need to, because we've got the same index again, we just need to write the square root and then multiply these two together. Now we just end up getting the square root of x squared minus 9x plus 3x, that's minus 6x minus 27. So I guess there's no real difference between these two forms. You could have it either way. But let's take a look at one more example similar to these two. Let's say we've got the fourth root of y over 5 multiplied by the fourth root of 7 over x. The same rule still applies. We've still got two fourth roots, so the result is just the fourth root. And now we multiply these two fractions together, so we just get 7y over 5x. So now what we'll look at is we'll look at how to simplify some radical expressions. Let's pan down. Suppose that we want to simplify the following radical expression, the square root of 20. Whenever you're trying to simplify an nth root, or I guess more specifically in this case a square root, we are going to consider perfect squares. So the perfect squares are like 1 squared, 2 squared, 3 squared, 4 squared, etc. And we know these equal 1, 4, 9, 16, etc. So basically, we look at this list of perfect squares. You may just have them memorized in your head, whichever is more convenient for you, and we see the largest of which of these squares is going to divide the number 20. And it turns out that the only perfect square which divides 20 in this list, or among all of the perfect squares, is the number 4. We kind of don't really care about the number 1 because it doesn't help us simplify. So the largest non-trivial perfect square that goes into 20 is 4, so we write the square root of 20 is the square root of 4 times 5. And then now, because we've got that property we wrote down over here, we've got this square root of 4 times 5, so we can split it up. We can look at it like we've got the left-hand side and split this up into 2 radicals like we've got in the formula on the left. So this becomes the square root of 4 times the square root of 5. And then the square root of 4 is just 2, and then the square root of 5 we can't simplify, so we just end up getting 2 times the square root of 5. So the square root of 20 is 2 square root 5. So that's one example. Let's take a look at one more. Let's say that we've got the how about the 4th root of 64. Well, that means that we have to find the highest 4th power which divides into 64. So the highest 4th powers, let's see what those are even. 1 to the 4th we don't really care about, but I'll list anyway. 2 to the 4th, 3 to the 4th, maybe I'll stop there. Let's see what we get for these. So 1 to the 4th is 1. 2 to the 4th is 2 times 2 times 2 times 2. 2 times 2 is 4. Times 2 again is 8. And then times 2 one more time is 16. So 2 to the 4th is 16. 3 to the 4th is 3 times 3 times 3 times 3. Or in other words, that's 9 times 9, which is 81. But anyway, we can already see that this is going over the value of 64 that we have here, so we kind of rule that out. It can't divide it if it's larger than it, right? So it turns out that 16 works nicely. 16 does divide into 64. So we can rewrite this as the 4th root of 16 times 4. Now, this is the square root, or sorry, the 4th root of 16 times the 4th root of 4. The 4th root of 16 we know is 2, because it was 2 to the 4th that gave us 16. It's the 4th root of 4. So we've simplified a couple of radical expressions, maybe just one more. Let's do a cube root. Let's say we want to simplify the cube root of 54. Well, I need to think of the perfect cubes, so suppose we've got 1 cubed, 2 cubed, 3 cubed, 4 cubed. Maybe I'll stop there, see if that's high enough. 1 cubed is 1, 2 cubed is 2 times 2 times 2 is 8, 3 cubed is 3 times 3 times 3, that's 27. 4 cubed is 4 times 4 times 4, that's 64. So we've got our list of perfect cubes. We see which of them, if any, that are less than 54 divide into 54. We've just got 1, 2, 3 of them, but this one doesn't really help us. 8 doesn't actually go into 54. You can double check that it doesn't. So the only option that could work is 27, and it turns out that 27 does work because 54 is 27 times 2. So you can write this as the cube root of 27 times 2. Or perhaps another way to write this is the cube root of 3 cubed times the cube root of 2. The cube root of 3 cubed, you can just imagine the cube root and the cube canceling, so we just have 3 times the cube root of 2. That is the same thing as the cube root of 54. So now that we've seen how to simplify some of these things, perhaps we should consider simplifying expressions that involve some variables as well, not only just integers. So that should be our last example. Let's suppose that we want to simplify something like, let's say we've got I forgot how I was numbering these examples. I don't even know whether I numbered. Yeah, I didn't really number these very well, but hopefully that's okay. So suppose we want to simplify the square root of x to the 7th, y to the 11th, z to the 9th. So if we simplify that, we're taking the square root of each thing involved, right? So if we take the square root of x to the 7th, ultimately we're just seeing how many times does 2, our index, go into 7? Well, it doesn't go into it evenly, right? Because 7 is odd, 2 is even, so it doesn't go into it evenly. But 2 goes into 7 3 times with a remainder of 1. So we can write this as, how about I'll do it like this. I'll write it as x to the 7 halves times y to the 11 halves. We're using the exponential form instead of the radical form. And then times z to the 9 over 2. Now we can think of these as x to the, how many times does 2 go into 7? It goes into it 3 times with a remainder of 1. So this is like 7 halves is the same thing as 3 1/2. Similarly, y to the 11 over 2 is the same thing as y to the 5th times y to the 1/2, because 11 over 2 is the same thing as 5 1/2. And lastly, z to the 9 halves is the same thing as z to the 4th times z to the 1/2. Now if we just want to write this back in radical notation, this would be x cubed times y to the 5th times z to the 4th times the square root. Now we take each of these guys and chuck them back under the square root. But in particular, we only take the base of each. We don't write the 1/2 as well, because the 1/2 is the square root. So we just get x, y, z on the inside. So this is our final answer. One more example before we go. Let's simplify the cube root of 16a to the 7th, b to the 14th. So now we've got a radical expression that involves a number and some variables, so it's a nice way to end. So we've already got our perfect cubes listed, so I'm going to scroll up a little bit to those. Where are those cube roots, or rather perfect cubes? Our perfect cubes are listed here. We've got 1, 8, 27, 64. Well, among those, the only number that could divide into it that would be helpful is 8. 8 does work. 8 goes into 16 twice. So we can write this as the cube root of 8 times 2. So the key was to pull out that 8. Now, we've still got a to the 7th. I'll break this up into more steps, times b to the 14th. Now, how many times does 3 go into 7? That's the question. So I guess before I do that, though, the cube root of 8 is 2, so I pull that out as 2. We've got the cube root, or I won't write the cube root yet, sorry. 3 goes into 7 twice, so we get a squared. 3 goes into 14 4 times, so we write b to the 4th. But we won't forget our remainders. Then we got times the cube root, and now we have to think, what were our remainders? Well, 3 goes into 7 twice with a remainder of 1, so we'll have a to the 1st power in this on the inside here. And then for b to the 14th, we see how many times does 3 go into 14? It goes in there. Oh, whoops, I have a blatant error here. Let me erase that before anybody else gets confused. My apologies. See, even I make mistakes. So, anyway, back where we left off. 3 goes into 7 twice, so we have 2 here with the remainder of 1, so that's like we have a power of 1 right here on the inside of the radical. And then 3 goes into 14 4 times with the remainder of 2, so we have b squared on the inside. So the remainder is what goes left over inside of the radical after simplifying. And then whatever you get when you divide it just comes out. So we got 3 goes into 7 twice, so it came out as 2 with the exponent. 3 goes into 14 4 times, so that's why that came out as 4 as the exponent. So anyway, this is our final answer. And this is the end of this video. I'm just going to pan out, briefly summarize what we've done. We've basically just learned the product rule for radicals and used that to help us simplify a variety of radical expressions involving multiplication. So I hope this video was helpful. In the next video, we're going to take a look at dividing radical expressions. So it's very similar. We're just going to learn maybe 1 or 2 tricks on top of what we learned so far. So anyway, I hope you all enjoy yourselves, and I'll see you in a future video.